Now we will start by considering examples of finding the potential of various continuous charge distributions, and we will start with the simplest one, which is the potential of a ring of charge at points on the axis of that ring, including the center. Before I talk about consider finding the potential of this ring, let me talk about a symmetry, which I call the ring symmetry, and this will help us actually find the electric potential whenever the charge is distributed over a ring, and even without carrying out the integration. So the topic is now what I call is the ring symmetry in potential calculation. To appreciate what this symmetry is, let me consider a ring of charge, and this is the center, and take this to be A, the radius of the ring, and let me have a charge and call this charge Q, a point charge at the ring, at the circumference of the ring, at one point here. Okay. Now, what is the potential of this charge at the center, which we call it in this case point P, for example? What is the electric potential of this Q at this point P? Well, V of Q in this case is equal to KQ over A, where A is the radius of the ring. Now, what if I have another point charge Q here? So if you like, call this Q1 and Q2. So this is VQ1. What about VQ2? VQ2 is also KQ2 over A. Take another charge, Q3. So VQ3 is equal KQ3 over A. Okay? And so on and so forth. Whatever you put here, okay, the charges in this case, the potential of any charge is just K multiplied by that charge divided by the radius. Now, if you have n charges, then in this case the potential is just V K Q I over I. So for n charges, point charges of course, V is equal sum over I from 1 to n K Q I over A. You just add up the potential of each charge, and you just and this will give you the potential at the center of the ring. Now, this is of course a scalar sum because the potential is a scalar. You know, it's not like in the electric field you have a direction here. It's just a scalar. So this is just an algebraic sum. Q's can be positive or negative. It doesn't make difference. Now, this is quite remarkable. What's remarkable about that is that in this case, this result is independent of how the charges are distributed over the ring. They can't be equally distributed. They can be all stuck or piled up in one portion of the ring or on another portion. This is completely irrelevant. This is completely irrelevant. The important thing is that they are just on the ring, okay? And that's what it is. Therefore, looking at this closely, we can write this as actually K over A, sum over I from 1 to n Qi. Now, what is this? Well, this is actually the total charge on the ring. So this is KQ over A, where Q is I from 1 to n Qi, total charge on the ring. And so we come to a very general result that if we have n point charges distributed over over a ring, okay, then the electric potential at the center of the ring is just simply the total charge. You sum them all, multiply by K over A. And this is what? This looks like the potential of a single point charge here. If you pile all these charges into a single point charge, which is equal to Q here, which is equal to the total charge on the whole ring, then the potential of all these charges on the ring is just equal to the potential of this point charge at the center. So this is a very general rule for the ring. So if you have how many point charges you have on a ring, irrelevant of their sizes or if their signs, the potential at the center is just their sum, the total charge, the net charge, multiplied by k over a, or that, put in other words, it is the potential of a single point charge having the total charge, having a magnitude equal to the sum of all the charges on the ring placed anywhere on the ring here. Okay, so the potential of that charge at the center. That's what the potential of all these point charges are equal to. So this is a very simple result that comes out from symmetry. Now we can extend this result not only to find the potential at points at the center of the ring. Actually, this applies also for the potential of any point on the axis of the ring. So if you have, for example, this ring here, and your point is here, this is your point P here, and you have charges distributed over the ring here, different Q's, okay? Then if you take this charge, call it Qi, now this is Ri, okay? And call this distance is A, and this distance is X. So X is how far is this point P along the axis of the ring from the center of the ring. Now note that Ri is equal to square root of a square plus x square. And this is the same for all the point charges here. So actually this is not Ri, this is just R. It doesn't depend on which charge you are talking about. This is the same for all charges. And so for example, V of Qi is just k Qi over R, which is k Qi over square root of x square plus a square. So this quantity, k over square root of x square plus a square, is the same for all the point charges. And therefore, if you want to find V total, in this case, for the all point charges, it is just, sum over I from 1 to n, V of Qi, and if you add up these together, then it is just k of square root of x square plus a square, sum over Qi from 1 to n, and this becomes kq over square root of x square plus a square, where q here is the total charge, the sum of all the charges carried by all the point charges on the ring. And therefore, this is just exactly the same as the result that we have derived here for the potential at the center of the ring. So even off the center, but along the axis of the ring, whether to this side or to this side, the electric potential of many point charges, no matter what the number is, no matter what the magnitudes are, the electric potential of these point charges at a point here is just equal to the potential of a single point charge, Q, placed wherever you like on the ring here, okay, and it has having the same magnitude, which is the sum of all these point charges, okay? And the expression is just kq over this distance, which is r, this distance r, okay? So that's the result which I call the ring symmetry. Now, with this result in hand, which is very simple to understand, of course, we can now move to the case when we don't have just point charges scattered over all the ring, but we have a charge continuously distributed over the whole ring, okay? In this case, what will be the the potential at the center of this ring? Let's see. So our question is, we have Q distributed over the ring. And so this is your ring, and you have this Q continuously distributed. The ring again has radius A, and I want to find the charge not just at the center. The center will be a special case, as we have seen, at a distance x along, this is the x-axis, along the axis of the ring. Now, if you do just a bit of thinking, and let me start with the case that the charge Q is uniformly distributed over that ring, okay? So this charge is uniformly distributed over the surface of the ring. Although this is not necessary, as we will see, but for the time being, for definiteness, let's assume that this is uniformly distributed over the surface, the length of the ring in this case. Now I want to find the potential of this continuous charge distribution at the center here, okay? So what I do in this case, as usual, I assume that this is split into small charge elements, which I call dq. I find dv, which is the potential of each of these dq, which is in my case, if you take this r, k dq over r. I note that this r is nothing but square root of x squared plus a squared, the radius. So k dq over square root of x squared plus a squared. And this is dv. And then I say, okay, then v is just integral over dv. And I continue substituting dq in terms of, you know, as usual, I write this just as we used to do in the case of the electric field. You express this in terms of the charge density multiplied by length, and then you carry out the integral. But actually, we don't need all that. If we just recall the ring symmetry that we have talked about, if you look at these, no, when you split this continuous charge distribution into small dq's, then you can consider each of these dq's as what? As a point charge. And so our result is very simple. It says, well, in this case, and each of these is a point charge, and I know that my result, the electric potential of a collection of point charges scattered over the ring, okay, is just k divided by square root of x squared plus a squared multiplied by the total charge of all these point charges, okay? And therefore, I would expect that this immediately should be equal to what? K q total divided by square root of x squared plus a squared. And this should be my result by just applying the symmetry that I have learned, the ring symmetry that I have just developed for individual point charges, but carrying it over to this situation when the charge is continuously distributed, and noting that when I split this into dq's, actually each dq can be treated as a point charge. So this is the result that I should get. So let's keep this and see that indeed, if we carry out the integral the way that we should do it formally, then we will get exactly the same result. I mean, there is no doubt that we'll do this. So to move on, we first identify what is our dq. Now, if q is uniformly distributed over the surface, over the ring, then in this case, there is a uniform linear charge density, which is equal q over 2 pi a in coulombs per meter. This is the charge per unit length. And so dq here is, this is ds if you like, is just k lambda ds over square root of x squared plus a squared. What is ds? This is the arc length. This is this arc length. And this arc length in this case corresponds, is subtended actually by an angle d theta. An angle d theta. So that's our dq. And I can substitute for ds in this case with what? I can substitute for ds r sorry, not r in this case, it's a d theta divided by square root of x square plus a square. So this is my dv. Now, v, integral over dv in this case, is just integration over this. Now, if you look here, k, lambda, a, x, and a, they are all constants for all the dq's, because each dq is at the same distance r from this point P, okay? And it has the same x and the same a. And therefore, the only variable in this case is just lambda a over square root of x square plus a square integral over d theta. And when you want to cover the whole, all the charges on the ring, you have to integrate over theta from 0 to 2 pi. Okay? And if you carry out this integral, the result is just 2 pi, as we know. So this becomes k lambda a 2 pi over square root of x square plus a square. Now, substitute for lambda q over 2 pi a, and this will cancel this 2 pi a, and so this becomes kq over square root of x square plus a square, which is just this expression that we have derived before without doing any integration, by just using the ring symmetry. Now, the ring symmetry, of course, can be extended actually to include disks and other surfaces, and we have an article about this that will appear in the video. You can refer to this for further details, and if you want to see how we can apply this ring symmetry at a larger scale.